Welcome to the deep dive. Today we're tackling, well, one of the biggest stories in the cosmos, the stellar life cycle.
It really is fundamental.
And looking through our source material for today, one thing just jumps out again and again. If you want to understand a star, how it lives, how long, how it dies, you basically need one key thing.
Its initial mass, right at the beginning.
Exactly. That mass sets the stage for, well, everything that follows, its whole cosmic journey.
That's definitely the core idea. So our mission today is sort of walk through that journey, from the places stars are born,
Stellar nurseries.
right, all the way to the end, the remnants. And we really want to focus on how stars are these incredible element factories for the universe.
Creating all this stuff heavier than hydrogen,
It's
basically?
pretty much everything, yes.
Okay, so to track all this, we need our map. We're going to keep coming back to the Hertzsprung-Russell diagram. The HR diagram is kind of essential for this.
Oh, absolutely. The HR diagram is elegant, really. It just plots how bright a star actually is, its luminosity against how hot its surface is.
And we measure that temperature with spectral types, right? O, B, A, F, G, K, M.
That's the sequence. O stars are the really hot blue ones. M stars are the cool, dim red ones. And the key thing is, a star doesn't just sit still on this diagram.
No, it moves.
It moves. It follows an evolutionary track across the diagram as it ages. And that tells us exactly what's happening inside.
Okay, let's unpack this then, starting right at the beginning. Where do stars actually come from?
They start in these vast, cold, dark places called giant molecular clouds.
And these things are enormous.
Huge. We're talking structures maybe over 100 light years across.
Yeah.
A good example is the Orion molecular cloud. It's about 1,500 light years away. And it holds maybe 200,000 times the mass of our sun in gas and dust.
So you've got this massive cloud. How does it go from that, just sort of floating there, to a star? Gravity must be the key player.
It is. It's this constant battle between gravity pulling inwards and the gas pressure pushing outwards.
Okay.
In the denser bits of the cloud, what we call cores, gravity eventually wins. It starts to overcome that internal pressure.
And things start collapsing.
Triggers a collapse, yeah. And as that clump of gas falls inward, it has to spin faster because of angular momentum conservation.
Like an ice skater pulling their arms in.
Exactly like that.
Mm.
And this forces the collapsing material into a flat spinning disk around the center.
The accretion disk.
That's it. And this disk feeds material onto the growing object at the center, the protostar, which isn't quite a star yet. It's mainly glowing from the heat of contraction.
Right, fusion hasn't started. But can we actually see this process happening? I mean, these protostars are usually buried deep inside those dusty clouds.
We don't see the protostar directly, usually, but we see the side effects. Astronomers find these things called Herbig-Haro objects, HH objects.
What are they?
They're these glowing knots of gas, and they're caused by incredibly high-speed jets of particles being shot out from the poles of the protostar.
Perpendicular to the disk.
Exactly, straight out, perpendicular to the disk. It's like the protostar is blasting away some of the material that's falling onto it. It's really dramatic visual proof of this messy formation stage.
Okay, so the protostar gathers mass, heats up. Eventually, it hits that magic moment and becomes a true star on the main sequence, like our sun. What defines that transition?
It's all about achieving balance, specifically hydrostatic equilibrium.
Hydrostatic equilibrium. Okay.
Yeah, the core finally gets hot enough, about 10 million Kelvin, to start stable nuclear fusion, turning hydrogen into helium.
And that fusion creates outward pressure.
Right. And that outward pressure from fusion perfectly balances the inward crush of gravity. The star settles down, finds its spot on the main sequence band of the HR diagram, and just stays there for most of its life.
But even on the main sequence, that initial mass is still crucial, right? It determines how the star fuses hydrogen.
Absolutely. It dictates the main fusion engine. For stars like our sun, and anything up to about, say, 1.5 times the sun's mass, low to intermediate mass, the dominant process is the proton-proton chain, the PP chain.
Which is basically just sticking protons together.
Essentially, yeah.
Yeah.
4 protons eventually become 1 helium-4 nucleus. And how fast this happens depends very strongly on temperature scales, like temperature to the 4th power.
But for the bigger stars, the ones more massive than 1.5 solar masses,
Sure.
cores are way hotter.
Much hotter. And that allows a different, more complex fusion process to take over the carbon-nitrogen-oxygen cycle, the CNO cycle.
CNO.
Here, carbon, nitrogen, and oxygen act like catalysts. They help the fusion of hydrogen into helium happen much, much faster, at those higher temperatures.
The end result is the same hydrogen to helium, but the mechanism is different and way more efficient at high temps.
Exactly.
And this leads to something really fundamental: the mass-luminosity relationship.
Ah, yes. This is key.
Because a more massive star has more gravity crushing down, its core has to be hotter to fight back.
Right, to maintain that hydrostatic equilibrium.
And a hotter core means a much, much higher rate of fusion. So the star is way brighter.
Dramatically brighter. Luminosity goes up really steeply with mass, roughly as mass to the power of like 3.5. A little bit more mass means a lot more light.
And that tells you how long the star is going to live. Because luminosity is basically how fast it's burning its fuel.
Precisely. It's the absolute decider of lifespan. If you're super luminous, you're burning through your hydrogen incredibly quickly.
So our sun, about one solar mass, gets around 10 billion years on the main sequence. Seems like a long time.
It is on human scales.
Yeah.
But let's compare it. This is where you really see the impact of mass, that aha moment.
Okay, hit me with the extremes.
Take a really massive O-type star. Let's say just 10 times the sun's mass. It's maybe tens of thousands of times more luminous.
Wow.
So it burns through its fuel incredibly fast. Its entire lifespan might only be 20 million years, maybe less.
20 million versus 10 billion. That's nothing, cosmically speaking.
The blink of an eye. Now go the other way. Look at a tiny red dwarf star, maybe only a tenth of the sun's mass, 0.1 emmer.
The M-types on the HR diagram.
Right. They are incredibly dim, sipping their hydrogen fuel extremely slowly. Plus, they're fully convective.
Meaning the whole star's material gets cycled through the core.
Yeah, they can basically use almost all their hydrogen fuel, not just what's initially in the core. So their predicted lifespan is, well, it's staggering.
How long?
We're talking maybe 10 trillion years.
Trillion, with a T.
Trillion. Far, far longer than the universe has even existed yet. They just burn so slowly. It really puts the sun's average lifespan in perspective.
It really does. Okay, so the sun is kind of middle of the road. Let's follow stars like it, the low to intermediate mass ones, when they finally use up the hydrogen in their core.
Okay, so core hydrogen runs out. Fusion stops in the center. Gravity immediately starts winning again, crushing the core.
Which heats it up.
Heats it up dramatically. And that heat becomes intense enough to ignite hydrogen fusion in a shell surrounding the now inert helium core.
Ah, so fusion moves outwards.
Right. And this shell fusion is actually generating even more energy than the core fusion did before. All that energy pushes the star's outer layers outwards, way outwards.
And that's the red giant phase.
That's the red giant phase. The star swells up enormously. Its radius might increase by a factor of 100 or more.
Whoa.
And as it expands, the surface cools down, becoming redder. So on the HR diagram, it moves up and to the right into the red giant region.
And for the sun, this means trouble for Earth.
Oh, yeah. In about 5 billion years, when the sun does this, its outer layers will almost certainly expand past Mercury, Venus, and probably engulf Earth, too.
Not great. Okay, so after the red giant phase, the star is burning helium in its core for a while, right? But what happens when that runs out?
For these lower mass stars, that's kind of the end of the fusion road. The core is now mostly carbon and oxygen.
Can't it fuse carbon?
It just doesn't have enough mass, enough gravity. It can't squeeze that carbon-oxygen core hard enough or make it hot enough to start carbon fusion.
So, no more energy generation.
Not from fusion. Instead, the star becomes unstable. It starts puffing off its outer layers through really strong stellar winds.
And this creates
a beautiful but very temporary structure called a planetary nebula. It's this expanding shell of glowing ionized gas surrounding the hot core.
heated by the core itself.
Exactly. They only last maybe 10,000 years or so, which is short in stellar terms.
Then what's left behind after the nebula disperses?
The exposed core. It cools and settles down to become a white dwarf.
A white dwarf.
Yeah.
Dense, small.
Incredibly dense. You've got roughly the mass of the sun crammed into a volume about the size of the Earth. It's mostly carbon and oxygen.
And it's not held up by heat pressure anymore, is it?
No, that's the fascinating part. It's supported by something called electron degeneracy pressure. It's a quantum mechanical effect. Basically, electrons resist being squeezed too close together.
Quantum physics holding up a star, and the density is just wild.
It's extreme. Like you said, a teaspoonful would weigh tons as much as a car on Earth.
But there's a limit to how much mass even this quantum pressure can support.
There is. It's called the Chandrasekhar limit. About 1.4 times the mass of the sun. If a white dwarf somehow gets heavier than that, well, The degeneracy pressure fails.
And it collapses further. We see these things,
Oh,
right?
yes. Sirius B, the companion star to Sirius, the brightest star in our night sky, is a classic white dwarf. We can study it quite well.
Okay, so that's the relatively peaceful end for sun-like stars, a quiet fade out as a white dwarf. But now, the big ones, stars born with more than, say, 8 times the sun's mass.
Their story is completely different.
Yeah.
Much more violent.
They also swell up, but even bigger.
Much bigger. They become red supergiants. Think of Betelgeuse and Orion. That's a famous example. Because they do have enough mass, enough gravity.
They can fuse heavier elements.
Exactly. After helium fuses to carbon and oxygen in the core contracts again, heats up, and starts fusing carbon into neon and magnesium. The neon fuses, then oxygen, then silicon.
Building up layers like an onion.
A giant cosmic onion, yeah. Each stage happens faster and faster at higher and higher temperatures, deeper in the core.
Until it hits a wall.
Until it hits iron. The core eventually becomes iron, and iron is special in a bad way for the star.
Why iron? What's the problem?
Iron has the most tightly bound nucleus of all elements. Fusing elements up to iron releases energy, but trying to fuse iron into anything heavier actually consumes energy. It takes energy in instead of giving it out.
So the star's furnace just shuts off instantly.
Pretty much. The moment the core is iron, there's no more energy being produced there to fight gravity. The star has run out of fuel, fundamentally.
And with no outward pressure.
Gravity wins.
Yeah.
Catastrophically. The iron core collapses inwards, unbelievably fast.
How fast?
In less than a second. It goes from something maybe the size of the Earth down to an object just a few kilometers across, maybe city-sized.
That's unimaginable speed and compression.
During this collapse, the pressure is so intense that protons and electrons are forced together to form neutrons, releasing this enormous burst of neutrinos.
Neutrinos. We actually detected those from a supernova, didn't we?
We did. Supernova 1987A in the Large Magellanic Cloud. The neutrino burst arrived a few hours before the light, exactly as the models predicted. It was a huge confirmation.
Okay, so the core collapses into this tiny, dense ball of neutrons. What happens to the rest of the star falling onto it?
That infalling material slams into the incredibly dense, rigid neutron core and rebounds. It creates this tremendous and powerful shock wave that blasts outwards through the star's outer layers.
And that is the supernova explosion. A Type 2 supernova.
That's the explosion, yeah. Tearing the star apart and shining brighter than billions of suns for a short time.
Incredible. And just like with the low-mass stars, what's left behind depends on the mass of that collapsed core.
Right. If the mass of that core remnant is between the Chandrasekhar limit, about 1.4 solar masses and maybe 2 or 3 solar masses.
It stays as that ball of neutrons.
Yes, it forms a neutron star. Held up by neutron degeneracy pressure, similar to electron degeneracy, but even stronger because neutrons can be packed tighter.
And the density must be even more insane than a white dwarf.
Off the charts. A single sugar cube of neutron star material would weigh about 1 billion tons on Earth. They're typically only about 10-20 kilometers across.
Tiny city-sized objects with more mass than the sun. Sometimes they spin really fast too, right? Pulsars?
Exactly. Many neutron stars spin rapidly and have intense magnetic fields, beaming out radiation. We see those as pulsars.
But what if the core is even heavier? Too heavy even for neutron degeneracy pressure.
If the remnant mass is above that limit, roughly 2 to 3 solar masses, the exact number is still a bit uncertain, then nothing we know of can stop the collapse.
Nothing.
Nothing. Gravity wins completely. The collapse continues, crushing the core down below a critical size called the Schwarzschild radius. And it forms a black hole.
An object whose gravity is so strong, not even light can escape?
That's the definition. We can't see them directly, of course, but we find them by their gravitational effects on things nearby, like watching stars orbit an invisible point.
Like the supermassive black hole at the center of our own Milky Way.
Precisely. About 4 million times the mass of the sun, sitting right there in the galactic center.
So we've gone from birth to death, white dwarfs, neutron stars, black holes. But what's truly fascinating here, as you said at the start, is that this whole process, especially the violent deaths of massive stars, is how we get the elements needed for life.
It really is the cosmic recycling program. Everything up to iron is steadily cooked inside massive stars during their lives, layer by layer.
Fusion factories.
Yep. But then, all the elements heavier than iron, things like gold, silver, platinum, uranium, they need even more extreme conditions.
Which they get in the supernova explosion itself.
That's part of it, yes. The incredible heat and flood of neutrons during the explosion allow for very rapid neutron capture the Carr process, which builds up these heavy nuclei.
So the explosion doesn't just destroy the star, it creates new heavy stuff.
It creates and disperses all that material, the hydrogen and helium that didn't fuse, the carbon, oxygen, iron cooked over millions of years, and the brand new heavy elements forged in the blast gets thrown out into space.
Seeding the interstellar medium.
Exactly, mixing with gas clouds, ready to form the next generation of stars and planets.
Which brings us back to Carl Sagan's famous line, "We are made of star stuff."
Literally. The nitrogen in your DNA, the calcium in your teeth, the iron in your blood, all of it was forged inside stars billions of years ago and scattered across the galaxy by supernovae.
It's an amazing connection. So we've really seen how that initial mass is the absolute key, dictating the star's entire life, its death, and its legacy, whether it fades as a white dwarf or explodes spectacularly.
And leaves behind either a neutron star or a black hole while enriching the cosmos.
But you mentioned the R process, the creation of the heaviest elements. Is the supernova story the whole story there?
Well, that's where things are getting really interesting lately. For a long time, supernovae were thought to be the main, maybe the only place the R process happens efficiently.
But maybe not.
Recent evidence, especially after we directly detected gravitational waves from merging neutron stars in 2017.
Ah, GW 170817.
That one. The light signature that followed that merger strongly suggested that these events, two neutron stars colliding, might actually be the dominant source of the heaviest R process elements, like gold and platinum.
Wow, so not just supernovae, but neutron star collisions might be where most of the gold comes from.
It's looking increasingly likely. The conditions in those mergers, the sheer density of neutrons flying around, seem perfect for the rapid neutron capture needed. It shows our understanding is still evolving.
That really changes the picture of cosmic chemical enrichment.
It does. Which leads to a final thought. As we keep finding these incredibly old, chemically simple dwarf galaxies, or study more of these neutron star merger events, what else are we going to learn?
About where the very first heavy elements came from, how the universe got seeded so early on.
Exactly. The story of element creation is definitely not finished yet. Something for you to mull over.